Welcome everyone. In this video lecture, we will see a very important relationship between diode saturation current, that is our IS, okay, and relationship between diode saturation current, cross-sectional area, and some other parameter like intrinsic carrier concentration, dP, dN, which is nothing but simply the diffusion constant for holes in the P-type, N-type silicon region, and diffusion constant of electrons in the p-type region. Similarly, Ln, Lp, the two important terms, diffusion length of electron in the p region, diffusion length of the holes in the n region. Q is the electronic charge, Na, Nd is the doping concentration of p side and n side respectively. So I have already written a very important relationship between the saturation current as a function of cross-sectional area A, electronic charge Q, Ni square, that is our intrinsic carrier concentration square, then dP by Lp, Nd plus Dn Ln by Na. So it is basically, I have taken this formula from the Sedra and Smith book, Microelectronics Circuits. Okay, it is very important, so that's why I have focused only on the equation. So the above equation gives a very simple observation, gives the relationship that is is directly proportional to the cross-sectional area. The diode saturation current is directly proportional to the area. Okay, means the saturation current is directly proportional to the cross sectional area. Okay, this one is the very first observation, that if the saturation current is proportional to area, is means the saturation current is proportional to area. The another observation is that the Is is proportional to the Ni square. We can say Is is proportional to the A. So this one is the saturation current proportional to the intrinsic carrier concentration. Ni is the intrinsic carrier concentration. Okay, concentration. So these are the very important thing. Means saturation current is proportional to the area, carrier concentration square, and Is A, Ni, and better to write this one Q, electronic charge. Okay, Q. Q is the electronic charge. Okay, so basically these are the three things. Okay, so first we have to focus about this Is. Is is proportional to the Is is proportional to the area. Okay, because in most of the problem we can see this kind of question will come. I will try to give one question related to this concept, means the saturation current proportional to area. So we have to find some other parameter value that we will put in a description, a numerical I have already made. So I will put that numerical based on this concept in description box. Okay, so Is is proportional to area. So sometimes this Is, here I am writing, this Is is proportional to area. So this one is sometimes called the scale current also. Scale current. Okay. So for example, if we say double the cross sectional area, if we say double the cross sectional area, okay, doubles the double the saturation current. Saturation current means the area will be increased, so saturation current is also double the value of is, which also result what, the diode equation. If you know the diode equation, the fundamental diode equation, id equals to is e to the power vd by eta vt. Okay, fundamental equation, the simplest one. Okay, so the if is is increasing, so id will be also increasing. So id, the diode current, okay, so the id value, the diode current also doubles for a given voltage. So diode current also double for a given forward voltage, that is our forward voltage, that is our vd. Okay, so this one is very important. Why I am focusing on this one? Because so many numerical is coming on this concept. In some cross sectional area is proportional to this much, so what should be the junction, what should be the saturation current, so it directly proportional. So this should be your is proportional, so that is our scale current. So if cross sectional area is double, okay, that is a is double, they double the saturation current, and it also double the diode current. Diode current is also doubles. Okay, because the area is increased all this. So that's why it is very important. Okay, in addition to that, now there are some terms. So this one is basically the important result that we have to remember. This expression is, so is is somehow, sometimes we can write like this: is is a function of a q ni square dp dn lp ln, and what we can say na nd expression. Okay, so now this is clear. Okay, so now some other terms that we have to know. So basically we have, I am focusing more on this one because so many numericals are there related to junction area. Okay, cross sectional area of the diode. Okay, so the other parameter also we have to know, so I am just writing the other parameter, what it signify, that dp. So the dp in the expression is nothing but simply diffusion constant. First write diffusion constant for holes. P is there, so for holes in the n type silicon region. Right. Okay. dP is the diffusion constant of holes in the n type silicon region. Okay. Just dn. So dn is simply diffusion constant for n is there. So we write electrons in the p type silicon region. Okay. Let's here once again. If this dp is there in the holes region, okay, diffusion constant of holes region in the n type silicon. Okay, dn is there, so diffusion constant for electron, okay, in p type region, clear. So this one is the thing. The other thing, that is our ln lp. So here I am writing ln is diffusion length. We are not going for the more details. Okay, for if you want to go for more detail, you can follow the microelectronics circuits book. diffusion length diffusion length of the electrons. Ln means diffusion length of the electrons in the p region. Okay, and Lp is the diffusion length of the hole in the n region. N region. Okay, this one is Ln diffusion length of the electrons in the p region, and Lp is the diffusion length of the hole in the n region. And Na and D is somehow common. Everyone knows, I think, Na and D. So this Na, Na is nothing but simply doping concentration. So I am writing doping concentration of the p side of the junction, and Nd is the doping concentration of the n side of the junction. No need to discuss. So basically, Is is proportional to A Ni square Q. Mainly we are focusing. So we have to, it is easy. Is is proportional to AQ Ni square. But other terms are also there. So I am just writing the facts. Okay. So here diffusion constant also we have heard, means for p type, n type diffusion, and L, this Ln Lp. For example, Lp. I am saying Lp is basically determines Lp, the diffusion length of the hole determines the stiffness of the exponential decay. Okay, means what it means as polar the value of Lp. If the value of Lp, that is our diffusion length of hole, is smaller, then it is faster, the faster the injected holes. Okay, faster the injected holes will recombine with the majority electron, with majority electrons. Okay, resulting in a steeper decay, resulting in a steeper decay of minority carrier concentration. Okay, so this is the all about this. So basically our concern is this Is is somehow function of A Q Ni square. In addition to that, some other function is there. So if you remember this simple terminology, you can say if saturation current is proportional to the area, charge, and intrinsic carrier current. In addition to that, some other parameters are also there. Okay, like dp by lp nd plus dn by ln na. But we are maximum time we are focusing. So I will try to give one numerical problem solved one. Okay, I have made a video on numerical problem based on is proportional to area. Okay, one numerical is there, so I will put in description box. You can go through that numerical, then more concept will be clear. So this is the relationship, means saturation current is proportional to the area. So if it doubles or 10 times, saturation current is 10 times. Okay, means area is 10 times. If cross sectional area is 10 times to the original one, so the saturation current is also the 10 times, and the corresponding diode current is also be 10 times. Okay, so this is all about this simple uh, relationship. So this is the relationship we have to Remember, some portion is this was is the fundamental relation, and it is from the microelectronics circuits book. So this is all about this uh, video. So thank you for watching this video.